In this video, we're going to look at how to write and interpret electron configurations. So electron configurations are essentially just the address of every electron in the atom. And this is what they look like. So the electron configuration for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The coefficient represents the energy level, the letter represents the orbital, and the exponent represents the number of electrons in that orbital on that energy level. When we look at potassium, you see the first energy level has 2 electrons. So the first energy level has 2 electrons. In this energy level, there's only one type of orbital, and that's an s orbital. So on the first energy level, the s orbital has 2 electrons. The second energy level has both s and p orbitals. So in the second energy level, there are 2 electrons in the s orbital, and there are 6 electrons in the p orbital. But if you count them, it's 6 plus 2, so a total of 8 in the second energy level. So here's the first. There's a second energy level, 2, 4, 6, 8. In the third energy level, you have s and p orbitals. There are 2 in the s orbital, and there are 6 in the p orbitals. So third energy level, a total of 6 plus 2, 2, 4, 6, 8 electrons. And then in the fourth energy level, in this particular atom, there's only an s orbital. There are no p in this particular atom because you don't have enough electrons. But if it was bigger, then you would have p, and you'd also have d orbitals. So fourth energy level, s, there's only 1 electron, and there it is, there's your 1 electron. There's another way to show the same thing. It's called an orbital diagram. And notice it's, 2 electrons in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, 6 in the 3p, and then 1 in the 4s. Notice how they are very similar. They correspond 1s2, 1s2, 2s2, 2s2. These arrows, they represent electrons. Okay, so here's your orbitals. You have the s orbital, you have the p orbital, and you have the d orbital. So the s orbitals are spherical shaped, the p are dumbbell shaped, and they go in the x, y, and z axis. So x is horizontal, y is up and down, and z is coming towards you and away from you. The d orbitals are a little bit more complex than that. And then the f orbitals, I don't show the f orbitals because they're very complex and we won't do a lot with the f's. If you imagine one of the Russian nesting dolls where you have a doll inside of a doll inside of a doll inside of a doll, that's how these atoms are. So you have, on the first energy level, you have s orbitals, but then on the second energy level, you have an s, and then you have 3p orbitals. The third energy level, you have, so atoms that are bigger, they'll have an s in the first, an s in the second, and then an s on the third. And they just basically stack on top of each other. It kind of looks like this. So just imagine the s orbital in the middle with another s and then your p's on top. So right here, we use the periodic table as a guide to help us write the electron configurations. And if you can imagine that this is the s block, this is the p block. Notice how helium is really associated with the s block. You have the d block, and then you have the f block. And this is a guide, so make sure you have this in your journal. This is going to be very important moving forward. So you take your periodic table and you just kind of overlay. And so we have our S, our P, our D, and then our F orbitals. So if we want to write the electron configuration for potassium, so here's potassium, it's right here. So what we have to know is that every orbital that is before the location on the periodic table for potassium, all of those are full. So we know the 1s orbital is full. Well, we only have 1, 2 possible electrons in the 1s. 1, there's 2. In the 2s, we have 2 possible locations. In the 2p, we have 1, 2, 3, 4, 5, 6. The 3s, we have 2. The 3p, we have 1, 2, 3, 4, 5, 6. And then over here, there are 2 possible, but since the location of potassium is right here, if you count, there's only 19 electrons total. Now, the bigger atoms, you'll use the d orbitals and the f orbitals. So potassium is like this. 1s2, 2s2, 2p6, and then 3s2, and then 3p6, because they're all full. Remember, they're all full. And then the final one, since potassium is in the first spot, we would say 4s1. And that's how you write it. Orbital diagram corresponds to it. So, yeah. Okay, now when you're doing this, you keep a couple things in mind. One, the Aufbau principle. Electrons fill the lowest possible energy levels before they fill the higher energy levels. And that's basically what we did just now. We utilized the fact that electrons fill the lower energy levels first. So 1s is lower than 2s, which is lower than 2p. So it goes in this order. And if you follow the periodic table from left to right and then go from top to bottom, it's basically you're following this 1s to 2s to 2p to 3s to 3p, on and on and on and on. Then you have the Pauli exclusion principle, which means that each orbital can only hold a maximum of 2 electrons, and they must have the opposite spin. So your arrows, that's what that was. Up spin, down spin. Now this is incorrect because you can't have 2 that have the same spin. But this one is correct because up spin, down spin, up spin, down spin. And notice that the p orbital, there are actually 3 p orbitals. Each of those hold 2 electrons. Hund's rule. An electron must occupy each orbital before a second can be added. So before we can go in and add additional electrons to our p orbitals here, like this is wrong because we have to add 1 in each, and then we can start doubling up. Now there's a shortcut. We're not going to use this shortcut very often, but this is called the noble gas configuration. And the shortcut goes like this. Since we know that neon and all the noble gases would have a full shell, full valence shell, then if we know in any atom that comes after that on that next energy level, we can just write neon because that's 1s2, 2s2, 2p6. We can write that instead of writing this whole thing out, which would be here. So sodium is 1s2, 2s2, 2p6, 3s1. Instead of writing all that out, we say, oh, the configuration for neon, 3s1.